So, good afternoon everyone. So, in this lecture I am going to continue my discussion on the solution to the optimal control systems. So, in today's lecture we will continue our solution methodology for optimal control problems, or let me call this as optimal control theory. So, this is the discussion that we are continuing since the last lecture. So, recall we were trying to note down the steps of the solution methodology for solving problems in optimal control theory via calculus of variation. So, recall my step 1. So, this was steps for solving optimal control problems. So, the step 1 was we assumed optimal conditions, assume optimal conditions, and so in this optimal condition we write down our performance index or the value or the functional at optimal values, and we also, so this is our performance index, and we also write down our plant condition. So, the plant condition at the optimal value, right. So, our plant condition. Okay. So, then the steps 2, the step 2 was we took our variations of the variables here are the state and the control variables. So, variations in control and so I would say set up variations in control and state variables. So, essentially wherever in our functional as well as the plant condition, wherever we have the state variables, we replace it by the state variable plus the perturbation, right, and then wherever we have control variable we replace it by the perturbed value of the control variable, right. So, we are writing it in optimal conditions. So, let me now denote with a star everywhere. Okay. So, we are perturbing at the optimal conditions. Okay. So, the star is at the original value. Okay. So, the step 3 was we write down our Jacobian for the optimal the functional for the optimal condition as well as the functional at the perturbed value. So, and further we introduce the constraint via the Lagrange multiplier. So, we introduce Lagrange multiplier lambda of t. So, that introduces this multiplier introduces the plant condition which is x dot is equal to f of x comma x dot comma t as, so plant condition as a holonomic non-holonomic constraint. Okay. So, non-holonomic constraint. Okay. So, then so this was where we stopped in the last lecture. We will continue our discussion for the next set of steps. So, step 4 is going to in the step 4 we write down our integrand for the functional at the optimal condition and the functional at the perturbed conditions, namely the Lagrangian. Okay. So, in step 4 we write down L of x star u star x, well the variables are x star u star t and we also write down So, this is at optimal. So, we write down the value of this Lagrangian at optimal conditions as well as at the perturbed condition, right. So, L becomes in our setup L is V. So, these are all at optimal conditions plus u star plus lambda comma lambda of t comma t, okay, plus we have these additional quantities. So, ds dt, this is our cost function plus lambda times lambda of t times the plant condition. So, f of x bar star x bar dot star u star t minus x bar dot star of t, right. Okay. So, we have now the next, we replace this total derivative of s by its partial derivative, which is partial s partial x evaluated at the starred or the optimal condition times x dot also evaluated at the optimal condition plus partial s partial t again evaluated at optimal condition. So, we have 4 terms in the Lagrangian. Then we again write down the value of this Lagrangian for the perturbed variables. The perturbed variables are the perturbed state and the control variables. So, similarly, we write down we call, so the perturbed Lagrangian L delta is L delta of x bar plus delta x star comma x bar dot star plus delta x dot comma u star plus delta u comma lambda comma t, right. And then we can always expand all these this perturbed Lagrangian. So, this becomes V of x bar plus delta x, this is a starred condition, comma u star plus delta u comma comma t, plus the rest of the values are the partial s partial x at the starred condition times x dot x bar dot at starred condition plus delta x. So, these are my perturbed values plus partial s partial t at starred condition plus what else have we got? Well, plus we have the plant condition as the constraint. So, lambda t, there is no, note that there is no perturbation in this quantity lambda, the Lagrange multiplier, times f of x bar star plus delta x u bar star plus delta u comma t minus the perturbed value of x dot star plus delta x dot. Okay. So, these are my perturbed values of Lagrangian, and then we have to write down the augmented performance index or for the perturbed value. So, we write down my augmented performance index or the functional first at the original value or the optimal value. So, J A of u star is integral T0 to Tf L dt, and the performance index at the perturbed value will be, well, let me call this perturbed value as any other value other than the optimal value. So, the perturbed value comes out to be integral T0 to Tf plus delta Tf. Notice that there is a perturbation in the integral as well, because the integral limits, because we are allowed to vary our integration limits, the upper limit, right. So, this becomes L delta dt, and then this integral can be broken down into two integrals as follows. And what we have is that so now notice that this particular the second integral, the range of integration is very small, namely delta t f. So, we assume that so in this small interval of integration in the second, let us say in this integral star, or let me call this as a, I can write down this Lagrangian, the perturbed value of the Lagrangian at its optimal value. So, what I have is the second integral becomes integral from T f to T f plus delta T f L delta dt, and this is L delta T f dt. This is also equal to. So, now we use our Taylor series approximation and expand our perturbed value of the Lagrangian at its optimal value up to first order. So, that is also equal to L at start condition plus partial L partial x, this is also at start condition times delta x plus partial L partial x dot at start condition times delta x dot, and plus notice that the only variables which are being perturbed are the state and the control variables. So, partial L partial u times delta u. Okay. So, that is it. So, all these derivatives are evaluated at the start condition times, notice that well. So, this will be, this is the integration from T f to T f plus delta T f. So, I have a quantity delta T f being multiplied. Okay. So, that is it. So, all now I have to do in which is in my next step is I have to take the perturbation of the perturbed performance index, or the difference of the perturbed performance index with the original index or the optimal index. So, we are trying to write down our conditions for the first variation equal to 0. So, step 4 was write down the Lagrangian, okay. And step 5, in step 5 I have evaluate the first variation, evaluate the first variation using Taylor series, right, and retain, we are going to retain order delta terms or the first order terms. So, my first variation delta of j is equal to j a at u minus the augmented index j a at delta u, right, well j a at u star. Okay. So, this becomes integral in the original interval of L delta minus L dt plus the integral from T f to T f plus delta T f. So, that was also L delta evaluated at well, this is L evaluated, not L delta, but L evaluated at T f. Notice, so this is our, well, we have taken L delta. Okay. So, this is L delta evaluated at T f times delta T f. Okay. So, then we have to expand all these terms. So, notice that the first integral we expand and see that the following terms arise. So, this is integral from T 0 to T f partial L partial x at the start condition delta x plus partial L partial x dot at start condition delta x dot plus partial L partial u times delta u, and this is also at the start condition, and this is all, notice that this is the variation up to first order times dt. So, we have taken the variation with respect to all the variables which are being perturbed, namely the state and the control variables, plus the term which is sitting outside the integral L delta at T f delta T f. And then notice that this quantity using my integration by parts will become partial L partial x dot delta x. So, this is at start condition delta x, and then minus. So, this is from T0 to Tf evaluation minus integral of from T0 to Tf partial t of partial L partial x dot, right, delta x times dt. Okay. Okay. So, then which means the next set of things that we do is we retain this integral terms all inside the integral and then see what happens. So, we are going to now write down the integral terms which are the underlying terms, this one and this one, and I see that this is also T0 to Tf partial L partial x minus d dt of partial L partial x dot at start condition. Then we have delta x dt and then plus partial L partial u at start condition delta u dt, right. And then, so this is all inside the integral, and then the quantities which are outside the integral are as follows. So, I have L delta at Tf evaluated at Tf times delta Tf, and then the additional quantity which is then written outside the integral partial L partial x dot at start condition delta x, right, and this is evaluated at Tf because delta x at the starting point T0 will be 0, we have fixed our starting time point. Okay. So, then I have to the next, so that is my step 5. My next step is to take the extremum, to set up the extremum and set up the conditions of the extremum and we see that when we do notice, let us look at the integration once more. Notice that our extremum will be 0, our first variation will be 0 when again we have the Euler Lagrange being satisfied. So, the underlying quantity plus an additional quantity which is the control derivative plus the sum of two quantities outside the integral which will contribute to our natural boundary condition. Okay. So, what we have is the following. So, if I choose my lambda, the Lagrange multiplier equal to lambda star, which is the optimal co-state function, then at optimal condition I see that first of all my Euler Lagrange equations are retrieved back, d dt of partial L partial x dot at start condition is equal to 0, and let me call this relation A, again my Euler Lagrange equation, and then since I have we also have the optimal control condition. So, we have another constraint that comes through. So, since my variation in u is arbitrary, I see that partial L partial u at start condition is also 0. Let me call this control condition as B. So, this is my control state condition, okay, and then all I am left with are the two terms which is sitting outside the integration limit. And so, let me write down these two remaining quantities. The first variation reduces to, well, let me write down step by step. So, it is L delta. So, L delta when written down in the form of a Taylor series are going to be L star at final time point times delta T f plus partial L partial x dot at start condition times delta x, right. Okay. So, these are my two terms, and we also have the plant condition, which is the non-holonomic constraint, and that can also be found using the Lagrange multiplier setup. So, my condition 1 or the plant condition can also be written using Lagrangian. So, we see that partial L partial lambda dot, well, partial L partial lambda at starred condition will give me 0. We are going to retrieve back our condition 1 from this condition, also known as, let me call this C as my co-state condition, or where co-state condition is the condition which retrieves back my Lagrange multiplier. And then, well, so what I have is, I have to finally process these two terms which remains, right. Well, these two also have to be set equal to 0, because these are the two terms that remain. Well, so to begin with the term that we have L delta. So, this is evaluated. So, L is nearly constant in this small interval. So, let me denote it by L star here, not L delta, because inside this small interval the Lagrangian is nearly constant, right. So, this is L star. Okay. So, now let us look at one more thing. Now, I need to write this bracketed quantity, this boxed quantity in a slightly more convenient form. To do that, let me see what is this, what are these variations, right. What are these variations? This is at delta T f. What are these variations? So, if my well, if my let me try to see how these curves look like. So, suppose from T 0 to T f I have let us say x 0 to my starting point for the optimal curve is as follows. So, this is my curve x star, and suppose the curve x star is being perturbed and it looks like the following, or let me draw a slightly simpler curve. So, this one, and let me call this as this one. So, slightly more simpler curve, right. So, my perturbed curve looks like the following. So, what I am trying to do is, I am trying to highlight the fact that delta x f, the variation at the final state variable, is not equal to delta x at T f. You will see that there is a slight variation, and that is why we need to be slightly careful. So, we need to write down this boxed relation in terms of delta x f. Okay. So, this is at T f. Okay. So, what we have is the following. We see that if this is my time point T f, and further I see that this quantity this gap between the optimal curve and the perturbed curve is going to denote as the variation in my state variable at time point T f. So, this is the variation at T f, and notice that if this following new time is T f plus delta T f, right. So, my variation delta x f is the perturbation from the optimal curve to the perturbed curve, right. So, there is a slight difference between the two quantities. In particular, we will see that so we will see that they are not equal, right. So, then so I am going to reformulate, let me call this as so I have D now, right. So, I am going to reformulate our relation D, noting the following. Note that my slope of the optimal curve is x bar dot star plus variation of x bar dot, and we see that this is almost equal to the value delta of x f minus the value delta. So, my so essentially this particular value minus this particular value, right. So, I see that this is also equal to delta x f minus delta x at T f divided by delta T f, right. So, change in the state variable divided by the change in time is going to give me the slope of the perturbed curve, or we can rewrite this quantity as follows. So, we can rewrite, so it implies that my delta x f is delta x at T f plus x dot plus delta x bar dot times delta T f, and we see that, notice that we have we are now going to throw away some higher order terms, especially the term delta square. So, this is almost equal to delta x f at T f plus x bar dot times delta T f, right. So, x bar dot, this is evaluated at the start condition. So, star, right, or in particular my delta x at T f is delta x at f minus x dot star times delta T f. The whole idea of rewriting this finding this relation is because we have a quantity sitting as variation of x at T f. We want to write it in the form of variation of x at f by noting this small relation between the two quantities. So, let me call this as d 1, and then I am going to rewrite d using this relation d 1 that I have found, and I come to a point that the new relation that I have is the following. So, this is L star minus partial L partial x bar dot, this is at the optimal condition, times x bar dot star, right, times well, this is evaluated at time point T f times delta T f plus partial L partial x bar dot star evaluated at T f times delta x f, okay, and this is set equal to 0. So, let me denote this as, notice that this is nothing but our natural boundary condition. Let me denote this by number. So, let me continue numbering something. So far we have numbered A, B, C, D. So, let me denote it by E. Okay. So, E is nothing but our natural boundary condition. So, now I have set up all my first variation conditions, namely the Euler Lagrange, the control condition, as well as finally the natural boundary condition, plus we have an extra condition in the form of a co-state condition, which is nothing but the plant condition. Okay. Well, it seems that this setup is quite complicated. So, let us slightly simplify this description by introducing our Hamiltonian formulation, or what we call as the Pontryagin H function. Okay.